Good morning, students. Chapter 7, System of Particles and Rotational Motion. Next topic in this chapter is angular momentum. Yes, rotational analog of force is taught. Similarly, rotational analog of linear momentum is angular momentum. Okay, here it is. Rotational analog of force is torque. Similarly, rotational analog of linear momentum is angular momentum. Okay. Again, first of all, we will see angular momentum of a particle. Angular momentum of a particle. Okay, angular momentum of a particle. For example, if it is x-axis, y-axis, origin, z-axis is perpendicular to what? Coming outside. Suppose I have one particle, here it is. Okay, with respect to point O, its position vector is, it is I. And yes, if it is performing circular motion about z-axis, if it is performing, yes, whenever object is performing rotational motion, each and every particle performs circular motion. So yes, this particle is performing circular motion in this direction. Clear? Okay. Now we know that linear velocity, it is in direction of tangent drawn at that point. So suppose particle is here. Okay, suppose particle is here. So its velocity will be in direction of tangent. Yes. So its linear momentum, that is p, it is also in the same direction. Yes. Let it is particle of mass m. So here how to write? As shown in figure, a particle of mass m. A particle of mass m is performing rotational motion. Okay, let its position vector with respect to O is R, and its linear momentum is P is equal to M. Yes, P is equal to MP. So direction of linear momentum is in direction of velocity. So yes, it is in this direction. Clear about this? Okay. Now, yes, as shown in figure, a particle of mass m, it is performing rotational motion with linear velocity p, with linear momentum p. So what is angular momentum of this particle and how it is defined? Yes, angular momentum of particle with respect to point O is defined as L is equal to R cross P. It is R cross P. Yes, it is definition of angular momentum. That angular momentum L is equal to R cross P. R position vector, P linear momentum. Okay. So yes, it is L is equal to R cross P. Its magnitude. How to write its magnitude? So yes, its magnitude is L is equal to RP sin theta. Where what is theta? So yes, here theta is angle between R and P. Yes, theta is angle between R. It is direction of R. Yes, sir. Okay, in this direction. So it is angle between R and P. Clear about this? It is angle between R and P. Okay, so yes, you have to remember what is theta. See, theta is simple. If R cross P is equal to RP sin theta, then theta is angle between the first two quantities. Okay. Now I can write this as L is equal to, it is P R sin theta. L is equal to, it is P R sin theta. Now again, remember theory of torque. See, here it is. If it is P, I draw line of action. If I draw line of action of P, okay, let this R is placed here. Okay, then yes, you have to draw one normal from point O to this line of action. Suppose it is N and it is perpendicular, for example, Okay, so what happens? See, what happens in this case? If this angle is theta, so obviously this angle will also become theta. And down. Okay, so yes, in such cases, what happens? You have to consider this triangle. Okay, in this triangle, take sin theta. If you take sin theta in this triangle, okay, sin theta. Then what is sin theta? Sin theta is equal to, it is opposite side, that is ON, upon adjacent side, hypotenuse, that is R. So ON is equal to, it is R sin theta. ON is equal to, it is R sin theta. So yes, ON is equal to, it is R sin theta. So here I can write L is equal to, it is P ON. Here what is L and what is P? See, this L is equal to, it is P, or I can write in terms of words. L is angular momentum. L is called angular momentum. P is called linear momentum. Okay, and ON is called perpendicular distance. So see, in this definition you have to remember. The angular momentum of particle L is equal to, it is P into ON, that is linear momentum into perpendicular distance. Clear about this? So yes, it is angular momentum. Yes, angular momentum is vector quantity. So how to find its direction? How to find direction of angular momentum? So yes, angular momentum is vector quantity. Its direction is perpendicular to R and P according to right hand thumb rule. What is right hand thumb rule? That you already know. What is right hand thumb rule? That you already clear about this. Okay, so yes, its direction is perpendicular to plane of R and P according to right hand thumb rule. Clear about this? Okay, now what about its unit? See, angular momentum is equal to linear momentum into distance. So its unit, J. What is unit of linear momentum? Yes, it is kg meter per second. And what is unit of distance? Yes, it is meter. So yes, it is simple, kg meter square per second. It is kg meter square per second. So it is unit of angular momentum. It is unit of angular momentum. Okay, that you have to remember. That is kg meter square per second. Okay, yes. Now next. See, it is angular momentum of a particle. It is angular momentum of a particle. If you are given more than one particles, then how to find? Angular momentum. Then how to find angular momentum? So angular momentum for system of particles. Angular momentum for system of particles. So see, that system of particles, total angular momentum L is equal to, it is L1 plus L2 plus L3 plus so on. So is equal to, it is L is equal to, it is R1 cross P1 plus R2 cross P2 plus S2 plus so on. So L is equal to, you can write it is sigma Ri cross P. It is Ri cross P. Clear about this? So yes, this equation you have to remember. It is angular momentum for system of particles. Clear about this? Okay. Now next theory. How to remember? Starting of next theory. You know that there is some relation between force and linear momentum. So now what is relation between torque and angular momentum? That we will see. Now next is relation between angular momentum and torque. See, here it is. Angular momentum, we know its equation. Angular momentum, L is equal to R cross P. Angular momentum L is equal to, it is R cross P. Okay. Differentiate this equation with respect to time. Differentiate with respect to time t. So yes, it is dl upon dt is equal to R cross P. R and P, they both depends on time. So yes, what is rule? Yes, we know rule. Again, first term as it is, differentiation of second term plus differentiation of first term, second term as it is. Clear about this? So yes, how to remember this differentiation? Whenever you are given two terms in multiplication, then what is rule? What is rule? See, first term as it is, differentiation of second term plus differentiation of first term, second term as it is. Okay, so yes, here it is dl upon dt is equal to R cross F plus dr upon dt upon dt, that is rate of change of linear momentum, means it is force. Dr upon dt means it is linear velocity. Here it is P. Clear about this? Now what about V cross P? So here V cross P is equal to, or if I want to write its magnitude, then it is Vp sine. Vp sine. See, V means linear velocity. V means linear velocity, and P is equal to mv, that is linear momentum. That is linear momentum. And we know that linear velocity and linear momentum, they have P and V are in same direction. They are in same direction. They are in same direction. So what happens? Mode of V cross P is equal to this Vp sine 0. V and P, they are in same direction, and whenever two vectors they are in same direction, their cross product will become 0. Their cross product will become 0. So yes, here what is answer of V cross P? It's 0. It's 0. So yes, therefore dl upon dt is equal to, it is R cross F plus F. Simple. So therefore dl upon dt is equal to only R cross F, and we know that what is R cross F? Yes, R cross F, it is torque. It is torque. So yes, it is one equation. That is dl upon dt is equal to torque. And how to write this in terms of equation? The time rate of change of angular momentum. Time rate of change of angular momentum is equal to torque acting on particle with respect to some point. Okay, and see, this equation is analogous to dp upon dt. dp upon dt is equal to f. Yes, this equation is analogous to dp upon dt is equal to f. Clear about this? So yes, it is one important question for this chapter. You have to obtain relation between angular momentum and torque. Or yes, you may also ask to prove this statement. Okay, prove that time rate of change of angular momentum is equal to torque acting on particle with respect to some point. Clear about this? So yes, you have to remember this equation, that is dl upon dt is equal to, it is torque. dl upon dt is equal to, it is torque. Clear about this? Okay, if I say torque is equal to 0, if torque acting on particle is equal to 0, then what happens? See, for example, if I say, okay, here, if tau is equal to 0, that is total torque acting on particle is 0. Torque acting on particle is 0. So therefore, according to this equation, dl upon dt is also 0. Yes, dl upon dt is 0, and therefore L is constant. L is constant. So what is meaning of this? Meaning is, whenever torque acting on particle is 0, its angular momentum does not change with time. Its angular momentum does not change with time, means it remains constant, and it is called law of conservation of angular momentum. Okay, when torque acting on particle is 0, its angular momentum does not change with time. Clear? Means it remains constant. Yes, means it remains constant. And it is called law of conservation of angular momentum. Clear about this? So yes, it is one extra point that you have to remember. You see, again it is analogous to, okay, whenever force is equal to 0, linear momentum is constant. Yes. So see, what is conclusion of this today's lecture? If you know the whole theory about torque, you can write easily about angular momentum. Then this theory, this point, okay, Okay, yes, this equation real upon dt is equal to tau, and this one law of conservation of angular momentum. If you know it from laws of motion for linear motion, you can easily remember for rotational motion. Clear about this? So yes, it is only for one particle. Now in next lecture we will see torque and angular momentum for system of particles. Okay, for today this is it. Next point is angular momentum for system of particles. See, for example, if x axis, y axis, origin, if I have numbers of particles, okay, and their position vectors are respectively r1, r2, r3 dash dash dash, their masses are m1, m2, m3 dash dash dash, their forces f1, f2, f3 dash dash dash, linear momentum p1, p2, p2 dash dash dash. Okay, then how to define total momentum of the system of particles with respect to this point O? Total angular momentum, total angular momentum of system, that is capital L, is equal to angular momentum of first particle plus angular momentum of second, angular momentum of third, etc., etc., etc. So I can write L is equal to it is R1 cross P1. Yes, we know definition of angular momentum for one particle, that is L is equal to R cross P. So L1 is equal to R1 cross P1. Position vector of first particle, linear momentum of first particle. Similarly, it is R2 cross P2 plus R3 cross P2, etc., etc., etc. Clear about this? So yes, how to write this again? L is equal to, I can write it as sigma Ri cross Pi. Ri cross Pi. L is equal to the sigma Ri cross Pi. Yes, I we have to take 1, 2, 3, 4, 5. Yes or no? Yes, it is. Clear about this? So how to find total angular momentum? Total angular momentum L is equal to the sigma Ri cross Pi. Or you can also write L is equal to it is sigma Li. It is sigma Li. Okay. Now see this equation. L is equal to sigma Ri cross Pi. So if I take differentiation of this equation, that is dl upon dt, that is dl upon dt. So obviously what I will get sigma Ri cross Pi. We have obtained its relation, and that is nothing but sigma tau. Sigma tau. Now what is sigma tau? Sigma tau is addition of two taus. Okay, that is tau internal and tau external. Tau internal is produced due to internal forces, and it is due to external forces. But according to Newton's third law of motion, we know that sigma F internal is equal to 0. Yes or no? So this tau internal, it also becomes 0. Because what is reason? Because these two forces will pass. These forces. Okay, it is one particle, it is second particle. See, these two forces passes from the points itself. So perpendicular distance will be 0. So torque will be 0. Okay. So yes, here this total torque is equal to tau internal plus tau external due to internal forces, external forces. They are on line joining two objects. That's why torque will become 0. Okay, torque will become 0. Tau internal will become 0. So here I can say that tau is equal to only tau external. Only tau external. So how to write this? Yes, dl upon dt is equal to, it is tau external only. It is tau external only. Clear about this? Clear about this? Okay, it is only tau external. It is only tau external. So yes, for system of particles, rate of change of total angular momentum is equal to total torque. Rate of change of total angular momentum. Total angular momentum is equal to total external torque. Total external torque on system. Total external torque on system. Clear about this? So tau is equal to, it is tau external. dl upon dt is equal to tau external. You have to take only external torque. Addition of external torque. Clear about this? Okay. Now again, if tau external is equal to 0, then L remains constant. Then L remains constant. So for system of particles, if total torque is 0, then its total angular momentum remains constant. So it is law of conservation of angular momentum for system of particles. So see, it is similar to system of particles is similar to for one particle. Clear about this? So it is one additional point that you have to remember. This one we have already discussed in law of conservation of linear momentum in this chapter. Okay, to write law of conservation of linear momentum, that is, see, dp upon dt is equal to, it is f. So this f is only f external. It is only f external. Okay. So yes, it is one additional topic that you have to remember, and this is it for today.